All right, so welcome to part 2 of the Natural Language Processing in Python video series. So if you have not seen part 1, there will be a link to part 1 in the description below, or you can just follow the playlist link to this video series. As usual, for every post, for every video in this series, there will be a corresponding blog post which can be accessed at my website. I'll leave a link to that post in the description below. Just very briefly, this page isn't quite up on my website yet. It will be when the video is posted, but this post, as before, each post will cover the content of the video, so everything that we go over will be elaborated on in this post if you want some more information or more detail. Similarly, if you want to see the code, just the code that is used in the video, I will as always be uploading that to my GitHub account here. So if you go to the link that I will provide in the description below, the code for that video will be found here on my GitHub. So you can access that instead of sitting there and typing out as you're watching the video. If you haven't seen part 1, just like I mentioned, there's a video and a blog companion post. So there's part 1 of this blog series for part 1 video that I did a couple days ago. So I'll continue this pattern as I release new natural language processing videos in Python. So with that said, let me just minimize this and let's continue on with part 2. So the first thing is we're going to start off by importing the natural language toolkit, and then we're also going to import the following function, which is called text, which is also from NLTK. So if you're not familiar with NLTK, or if you don't know what these lines, if they don't look familiar to you, I would say consult part 1, where we go over installing NLTK and also describing what these lines do. Just very briefly, we're creating an object here, Alice, which is taking in what a text function returns. The text function basically just takes some body of text and makes it understandable to NLTK, and then we're creating a frequency distribution using NLTK's freq_dist function, and we're just passing in the text that NLTK understands into this function, and then we're going to be using that in a little bit. So again, if those lines look a little bit foreign to you, consult part 1. Otherwise, let's continue on with part 2. So I guess I want to pepper in a few different natural language processing terms as we go along here. I will pepper them in from time to time to reduce overwhelm, so that way you don't have to learn all of these odd vocabulary words all at once. So the two that we'll be focusing on here are hapaxes and collocations. So the first hapax is basically just a word that occurs only once, exactly once, in a body of text. So there's the Wikipedia link above this line, which prints out the hapaxes of the frequency distribution object that we created above. So if we go ahead and run this, let's just do 2 here. So if we run this here, we'll get a list of all of the words in Alice in Wonderland that are used only once. So some of these, there could be, for instance, let's see, pocket. Pocket may be used more than once. It's only used once if it's capitalized. So if you wanted to, for instance, only care about the case when the word pocket is used irrespective of case, it's pretty easy to filter that out if that's what you care about. If you do care about case, if that does make a difference, then this initial hapaxes function will give you what you expect. So I'm just going to go back to the code there. So the next term that I want to introduce is collocation, and this is a pair of words or a group of words that are generally next to each other, juxtaposed. So an example might be red wine. You usually see red preceding the word wine or white wine. If you look for collocations in Alice in Wonderland, one such pair of words may be something like red queen or white rabbit, which are predominant characters in the Alice in Wonderland text. So if I go ahead and let's, I guess, comment out this line here and spell print correctly. Let's see. There we go, spell print. Okay, so then we'll run that. And if we print out the collocations here, we'll see, let's see, do we see white rabbit? Yes, we do. So white rabbit is a collocation, and that is listed here in this list of collocations. So I'm just going to leave those there, and we're going to proceed on to the main focus of this video, which is going to be accessing different types of text. So we predominantly, so far, at least in part 1, have focused on accessing resources provided by the Gutenberg library or the Gutenberg project. So Project Gutenberg, as I mentioned before, is this collection of works that are provided for free in the public domain, and NLTK provides kind of a wrapper or an API for us to access that work. So you'll probably recall that you did this line in part 1 where you downloaded all of these different types of text resources that NLTK can access. So we're going to go over a little bit more about Project Gutenberg and how to access some of the other components of text resources provided by Gutenberg, and then we'll look at some of the other text resources that were also included in this download dialog box that you went through and downloaded. So there's a few other things that we can do for text obtained from Gutenberg. This actually will be somewhat similar to manipulating text from other resources as well. So for instance, if we just care about the words in a given text, we can say nlt.corpus.gutenberg.words, and we can give it the name of the text that we want to use. In this case, again, this is Alice in Wonderland. You can use any of the text names that are provided from the file IDs. So if you recall in the first video, we looped over all of the file IDs of what the Gutenberg corpus provides to us via NLTK, and so you can put any string argument here that corresponds to a title from this repository. So if we print these words out, let's go ahead and do that. So if we print these words out, we'll get a list. Now this list is quite short. The reason for that is Python doesn't want to print out the entire list. You'll see an ellipsis there at the end of the list. I'm pointing to the screen. I don't know why I'm pointing to the screen. You can't see me do that. But anyway, so the list here is shortened. The list is much longer, of course, because the number of words in Alice in Wonderland is more than 4. So anyway, that's just, it's automatically making it a bit more concise so it doesn't dominate your screen. So I'm just going to go ahead and comment that out. Just like with words, you can also extract the individual characters of a text. So this is a very similar pattern to what we saw above with extracting the words, only now instead of .words, you'll see here that we're using .raw. So likewise, if we go ahead and print this out instead, the terminal, we'll get, well, pretty much the entire text of Alice in Wonderland, but the object that we get from processing this raw thing that we pass into this function will give us the characters, so we can process those for whatever purposes we wish to process. The final thing is we may want to get text in terms of the sentences. So again, a very similar pattern. If we just care about the sentence, so we'll get a list back from this function that will give us each component in the list will be a sentence from Alice in Wonderland in this case. So if we go ahead and run this, we'll see, again, a list that has an ellipsis there because it doesn't want to bombard the output to the screen, but we can see that it's a list of lists where each element in the list is a sentence in the text that we feed in. So I'm just going to go ahead and comment that out as well so we don't get that printing every time. So let's move along here. So there's a few things that we can do now that we have access to the characters, the words, and the sentences of a text. And this is, of course, also applicable to any other text that you can manipulate via the Gutenberg NLTK module. So one thing that we can do is we can do something like calculating the average word length. So the way that we would do that is we could take, if we can extract all of the characters, as we did, we set this into a variable called AliceChars, and if we can extract all of the words in Alice in Wonderland, which is Alice_words, then what we can do is we can just divide the length of the characters by the length of the words, of course converting that to an int, so that way we, if we get a division with a remainder, it rounds. So if we print that out, we'll get an average word length for the text. Similarly, we can also find the average sentence length doing a very similar type of thing, only now we're dividing the number of words with the number of sentences in the text. So we can go ahead and print this out to the screen to see what those numbers are. So 4 is the average number of words in Alice in Wonderland. So each word is on average of length 4, and then the average length of sentence in Alice in Wonderland is on average of length 20, so 20 words on average. So I'm just going to go ahead and comment these out so they don't print out every time. Oops. So I guess just to make it a little bit easier for ourselves, because we'll probably make use of these in the future, we can define 2 functions which do exactly what we printed out there, only they're more broad in terms of their applicability. They can be used for any text that we feed in. So we can define a function called average word length that takes in the number of characters and the number of words, and then we just return the division of those things. Similarly, we can do the same thing with average sentence length. So we're just really wrapping up the logic that was provided in these two lines, or in these two print statements anyway, and we're moving that into two different functions. So let's go ahead and use those functions. One thing we can do is we can loop through all of the text in Project Gutenberg, and we can say, all right, give me, or us, the average sentence length and the average word length of every single text in this corpus. So what we're doing is first we're going to loop through all of the file IDs. So if this looks not familiar to you, consult part 1 of the tutorial where we loop over file IDs for any type of written work from NLTK. So we're looping through essentially all of the files that Project Gutenberg provides to us via NLTK. We're essentially determining the number of characters, words, and sentences of each work. So we're saying it's essentially the exact same thing that we did up here. We're just taking the length of the characters, because we're using .raw, words, and sentences.sense. And then what we're doing is we're just printing out to the screen that this file ID, so this is the name of the text that we're currently considering, has an average word length of the function call average word length, and then also has this average sentence length of this function here. So if you print this out, we're going to get a loop that's going to go over all of the text and give us an average word length and an average sentence length for each piece of text. Okay, so let's go ahead and run this thing. So I will run it there. And as we run, we'll see the name of the text file obtained from Project Gutenberg, and we'll see the average word length and the average sentence length of each work. So what's interesting kind of to note from this is that every piece of work that we've considered in this data set has an average word length of 4. It's kind of neat. And it looks like the longest sentence length is Milton's Paradise, and the shortest one appears to be Shakespeare's Caesar. So kind of an interesting data point there. There's a lot more to play around with in terms of analyzing these sorts of things, but I guess for the sake of time, I'm just going to leave that as it is. I'm just going to comment this out so it doesn't print out every single time here, and move on. So one thing that you probably notice about Project Gutenberg, at least when we access it via NLTK, is that the file IDs, the amount of works, are only kind of a limited subset of what's actually provided on Project Gutenberg. If you've ever been on the website before, there's a ton of books on there. Project Gutenberg is not limited to just what we saw there, 15 titles. It has many, many more public domain works. And all of those works are accessible via the website. So what we're going to do is we want to find some way to extract text information online. In this case, we'll be navigating to the text information found at Project Gutenberg, but this method will be broadly applicable to any time you want to access solely text information from the web. And what we're going to do to access that information is use URL lib. So this module will most likely be installed on your machine. If not, go ahead and run pip install URL lib, so that way you can follow along with this. So this will be used to navigate to the website where the text for a given book is located. So say I want to download the text for The Picture of Dorian Gray by Oscar Wilde. This is not provided from NLTK directly, so I'm going to have to go on Project Gutenberg, find where this is hosted, and download it. So wouldn't you know that I have a variable here called URL, and this is the link to where the text of this book is located. So let me just open that up here. So this is the corresponding URL of the book. Actually, if I go back, let's see, I think I had a tab open. If I go back here, so if you go to Project Gutenberg, and if you look for any piece of work, so just I guess this is useful if you don't care about analyzing, let's say, The Picture of Dorian Gray, but you want to analyze some other work that's not accessible through NLTK, but is on Project Gutenberg. You can search, let's just say, Oscar Wilde, and then you can find the piece of work that you actually care about. Again, for us, this was Picture of Dorian Gray. And every book is going to have something that looks like this. It's going to have the HTML, the book in HTML format, EPUB, Kindle, if you want to put it on your Kindle, and then also plain text, which is the source that we care about. So if you click on that, that will take you directly to the link that hosts the text portion of the book, and that's what we're going to be processing. So I'm just going to minimize that. So again, the variable URL stores the link to where this is stored. And then what we're going to do is we're just going to declare a variable called raw, and we're going to tell it to open the URL, read it, and then decode it. So this decoding is just to make sure that the content that is read from this website is decoded in UTF-8 format. So if you don't know what that means, it's okay. It just essentially makes it a string and makes it easy for us to process as a string and do NLTK things to this string. So if you do that, that will give you essentially the whole text for Dorian Gray in this variable raw. So once we have that, we can actually convert it to something that NLTK can understand, because now we just have essentially this raw object, which is really just a string, but we want to convert it so that way we can play around with the natural language processing of this particular work. So let's create a variable called Dorian Gray, and then we can do something familiar to what you've seen before. We'll use the NLTK text function, pass in the raw data, and what we're actually going to do to the raw data is tokenize it. So this is a little bit different than what you've seen when we did with this with Alice in Wonderland, since we were reading it directly in from the Gutenberg corpus. Now we're tokenizing raw text we've downloaded from the internet, and then we're converting it to a NLTK text object. So this NLTK text object that we get in this Dorian Gray variable behaves just as you would expect. If you followed along with the previous tutorial, we can create frequency distributions and get average lengths of words, average lengths of sentences, and all that good stuff. So actually, just to kind of hammer that home, one thing we can do is we can create this frequency distribution based on the content that we have here. So we have fdist Dorian, which we're just passing in this NLTK text object to the frequency distribution function. And then just like we saw in the earlier part of this video, we can compute the hapaxes, the words that only occur one time in a written work, and we can print those out to the screen. So let's go ahead and do that. So what this is doing is this is actually navigating to the website where the picture of Dorian Gray is hosted. It's pulling in that data, it's converting it to something that NLTK can understand, and then it's getting this, which is the list of hapaxes in picture of Dorian Gray. So that's that. I'm just going to comment that out. And as I mentioned before, this is not limited to just this work. If you want to download or follow this approach, process some type of text on any other site that happens to be in a format like this, where it's just text, you can use this approach and it should work. So let's just continue on here. So we're going to consider another type of text resource that NLTK allows us to process, and this is web text. So just like we had the Gutenberg set of text data, we can process text that NLTK provides to us that came from the web. So let's go ahead and take a look at what type of data that is. So what I'm going to do here is I'm going to loop through the web text file IDs. So this is similar to what we did when we were looping through the file IDs for Gutenberg, where this gave us a list of all of the text that Gutenberg has. Here we'll see all of the names of the text files that the web text NLTK dataset provides to us. So let's go ahead and run this and see what we see. So we have a couple files here: firefox.txt, Grail, overheard, pirates, singles, and wine. And if you want more information about what each of those text files consists of, there's a link here where it provides a little bit more information on each one. Very briefly, if any of these sound of interest to you, then by all means try to experiment with any one of these text files further. So firefox.txt, this is basically just someone went to the Firefox support forum, pulled all of the data from that, all the text data, and then just put it into a big data set. Grail.txt, this is the movie script from Monty Python, The Holy Grail. It's a great movie. Overheard, this is somehow a compiled text of conversations that were overheard in New York with some, I guess, information that's sensitive omitted probably. Pirates of the Caribbean movie script is there. Singles, this is directly from Singles ads. That's probably an interesting one to parse. Wine.txt, these are reviews for wines from Fine Wine Diary. So a couple of interesting data sets there. If any of those catch your fancy, then by all means try to play around with any one of those. I guess just to give you a sense of what you can do with any of these, you can manipulate these in the same way that we've done for any of the things that we've obtained from the Gutenberg corpus. So what's kind of nice about that, let me just comment this out. while I'm talking. What's kind of nice about that is that we can extend the same type of logic that we've used to the web text. So let me just uncomment these and kind of show you what I mean. So what I'm doing here in these 3 lines is I'm extracting the number of words, the number of characters, and the number of sentences from Monty Python and the Holy Grail. So I'm extracting the web text words of grail.txt raw, which corresponds to the number of characters, and sentences, or corresponds to the characters and sentences. I'm taking the length of all of those things and I'm just storing them in 3 respective variables. So just like we did with the Gutenberg corpus, we can do the same thing with the web text corpus. And I'm calling the functions that we previously wrote, average word length and average sentence length, and I'm running those functions on what I've obtained here from the Grail. So let me go ahead and run this here. We'll see what we see. And we have 3 and 9. So the average word length actually in Monty Python the Holy Grail is 1 character less than it is for all of the other books we were looking at, and the average sentence length is of length 9. So kind of neat, and it's really just kind of neat that you can apply the same sort of logic to any of these other corpuses that are provided by NLTK. I guess I'll leave those. So let me just move along right here. So another corpus that we're going to consider is the corpus of inaugural addresses. So when a president becomes president of the United States, they have to make a speech, and that is called their inaugural address. So this is a collection of all of the inaugural addresses from all of the presidents, and basically it's just, you know, the text from each of these, the transcriptions of each of these addresses. So again, just like we did before for the web text, let's go ahead and print out the files that come with this. So I'm just going to write that and run it here. So what we're going to see are the names of the text files that we can process. What you'll see, the pattern here is there's a year, a dash, and then the last name of the president.txt. So let's go ahead and go back. So I'm just printing those out in the same way that I did for all of the other ones. The only change here is the corpus that we're considering, which in this case is .inaugural. And then I'm just printing out the text files of each of those. So let's comment that out. And as I mentioned, I guess this comment is basically just elaborating on the format of each of the text files. And let's see, I guess for fun, we can loop through each of the addresses. And then one thing we can do is we can loop through and keep track of the number of times a certain word is used in each address. Let's say we want to figure out how many times, or how many times is the word America or Americans or American, how many times is that word used in each of the addresses of each of the presidents? So what we can do, let me just comment this out here, we'll step through it. This basically does exactly that. What we do first in this line here is we loop through all of the file IDs. This is exactly what we did on line 261 and 262. So we're looping through all of those, and we're going to start a variable called America count, which is just going to be defined here, and then every time we consider a new speech, it's going to refresh back to 0. So inside of this loop, we're going to loop through all of the words in each of the addresses. So the first loop, looping through all of the text files. Second loop, looping through all of the words in each of the text files. And then what we want to do is check, do any of the words that this particular president used in their address, do they start with the words America? So again, this can include America, American, Americans, anything like that. And what we're going to do is we're going to check by doing these 2 lines here. So we're going to say for the word that we're currently on, convert it to lowercase just so we can kind of make everything uniform. And then does that word start with America? So this just helps us to not have to check, does it start with America? Does it start with like America with an uppercase A? This way, if we lowercase everything, it just makes it very easy to check one thing. And then if it does, what we'll do is we'll increase the America count by 1. And then on each loop, after we complete the loop for a particular president, we'll output just some information based on the America count. So we'll say this president, this guy. So what I'm doing here for president and year, I'm extracting the information from the text file. So this president variable is obtained because everything after the dash, so there's a 4-digit year, and then everything after that dash is the name. That's how I'm extracting the name of the president. And then also the year is the first 4 characters of the name of the string. So I'm extracting that way. So I'm just saying president president of year, said America this many times. So let's go ahead and run that and see who said America, who loved America the most. So, okay, let's see. So we got a lot of output here. Looks like, oh man, Jackson's just not very patriotic. Adams, not patriotic either. Let's see here. Bush 30 times, very American man. Clinton 33 times. I think that's the most. Right, so that might be great if we're just looking at one word or a small data set. But if we wanted to take this example and make it a little bit more complicated, for instance, let's say instead of just America, I want to figure out if, I guess, the word citizen is used and how many times it's used in each speech. So you could also do something similar. You could tweak the above code to do exactly that, but it's a little bit harder to do once you have more words and once you're looking at a larger data set. So maybe one thing that might make sense is to think about how we can make this more visual. So can we plot this information, and also what tools can we use to make that a little bit more, I guess, visually concise, so it's easier to pick up on, certain patterns or trends. So the one tool that we're going to use to do that is we're going to consider something called a conditional frequency distribution. So before in part one, we mentioned the frequency distribution functionality that NLTK provides using the freqdist function. So a conditional frequency distribution is really just a collection of frequency distributions that are run under different conditions, different things that we care about. So as you recall, the freqdist function, we just gave it a list as input and it created this distribution for us. So for NLTK, it provides also an analogous function called conditional freqdist. And instead of taking a list, it takes a list of pairs. And each pair on that list is going to have the form of condition event. So what is the condition in our case? Well, in our example, we care about the case when either the word, let's say America or American or Americans, is used. Let's also say that we care about the word citizen. Or, again, citizen or citizens, plural. Let's say we care about those. Those are our conditions. And basically those conditions will be paired with the event of the year. So the year corresponds to the year that the speech was given. And the events, those are the events, and the conditions are the words that we are looking for. So we can create a frequency distribution object in NLTK using this information. And it's going to be pretty similar to what we did in the above code, where we just had this series of nested loops where we were looking for, in that case, the word American. In this case, it's going to be a very similar approach. Essentially, you can take a look at these three loops here, these three lines, and those are very similar to what we saw above. Let me just go above again just to kind of give a sense. So we had this first loop, which was looping through the text files, which contain the inaugural addresses. The second loop, which contains this loop that's looping over all of the words in each address. So we have both of those loops present in this frequency distribution function. So that's this loop here and this one. And then we're also looping through the words that we care about. In this case, it's not just America, but it's also citizen. And then we have an if condition. This if condition is almost exactly the same as what we saw above as well. We're asking if the word, the lowercase word, if any of the words in the text that we're currently processing start with any of the words in our target list, namely America and citizen. So if that condition is true, again, the target here is the condition event, we want to pair that with the event, which is the year. So the year is the year in which the presidential inaugural address was given. And so what we're going to get as we feed this into the conditional freqdist function is a conditional frequency distribution object that we can treat just like we did, almost similarly to what we did with the frequency distribution object that we did when we were processing text from Alice in Wonderland. And we can plot the information that we get back from this. So let's go ahead and write this and give it a run and see what we see. So if we run this, we should see a plot. I guess I forgot to comment that out there, so it printed that out again. But we see this figure here, which is a plot where on the x-axis we have the events or the years. So all the way from 1789 to 2009. This is a little bit not quite up to date. And then we have the occurrences or the counts, or I guess in other words, the conditions that we care about. Again, the mentions of America or citizen. So orange is citizen and America is blue. So you see a big spike here for both America and Citizen, or at least a very big spike for Citizen and a somewhat smaller spike for America here in this year. So that's kind of interesting. And it's a little bit easier to just visually look at this plot and walk away with some information that might be a little bit harder if you're just looking at the text output of this. So the plot might be a little bit more useful for your purposes depending on whatever they may be. So that's, let's see, I think I need to close that. There we go. So that's pretty much it for this video tutorial. We'll continue on in the next part of natural language processing, where we'll be considering generating word clouds. So thanks again for watching and have a great day.